Hi everyone, welcome to ApacheCon 2021. I'm very happy to be here. Before I start, I want to share a very common problem in analyzing real-time data. Almost all analytical platforms have these things in common. First, the data need to be transformed and ingested from the source to any of the analytical platform. Based on the capability, there could be multiple analytical platforms. For example, for batch, there will be one platform. For streaming, there will be another platform. Once the data is loaded, there will be other apps like reporting tool, BI tools, which consume this data from it. Always, business needs are really demanding, and there is always need for fresh data as much as possible for their analysis. However, in order to do that, we usually use a lot of components. And I believe most of us were there before, face the same challenge in managing these components to work reliably and nothing fails, etc. On top of that, things will get more critical when the need is real time. Any failure in ingestion are also critical. How do we solve this problem? Would you have asked this? Today, we are going to discuss Apache Druid real-time ingestion and best practice. So our main focus is on the ingestion part, this part. Who am I? I'm Tijo Thomas. I'm solution architect at Imply. I started my big data journey from 2013 onwards. On this journey, I worked at Huawei, Hortonworks, Cloudera, now at Imply. A little bit background of Imply. Imply was founded by original creator of Apache Druid. We provide managed service for Druid platform in cloud, Kubernetes, on-prem, and provide a BI tool called Pivot, optimized heavily for Druid kind of workload, and also a APM cloud called Clarity, a monitoring tool and other related tools for operation. For those who are not familiar with Druid, let me start off with explaining what is Druid. What is Druid? Druid is a open source, definitely. It's an Apache project. It's a high performance, column oriented, distributed data store. High performance means low query latency, high ingestion rate. Column oriented, it better possible scan rate. Distributed, it can be scaled to hundreds to thousands of nodes. And it's a data store. It's a cluster architecture. A copy of the data is stored locally and query from it. This is one of the reasons Druid is very fast when compared to other analytical platforms. For those who are new to Druid, I will take a minute to explain the Druid architecture and its component. We have query node, data node, and master node. These are the three components I would like to explain a little more in detail. Master node have coordinator service, which coordinate and manage all the historical data. Overload service manages the ingestion part of it. Query node accept the query, split it into multiple subqueries and send it to the node, data node. And once it received the result from the data node, it merged the result and send it to the client. Data node has two jobs. One of the service is middle manager service, is responsible to query the real-time data, and at the same time, it has also the responsibility to ingest the data. Whereas the historical service responds to queries, subqueries, historical queries. The topic for this session is about the challenges and best practices on Druid real-time ingestion. Before we dive deep, we will see how the real-time ingestion works. Here, the middle manager reads the data from Kafka and store internally. So you have data here in broker, and it's gets stored to middle manager. After collecting sufficient data, it pushes the data from the middle manager to a deep storage. Deep storage is a kind of storage, archival kind of storage. It can be S3, HDFS, or NFS, or any of those sort of storage. Once the data is moved there, historical picks this segment from the deep storage and it load it locally to its node. Okay. Going further deep, let's discuss how middle manager reads from Kafka. Middle managers spin up a peon or worker task, and the Kafka consumer, which is a Kafka client library, within the task reads the data from Kafka partition. Here are the steps. Middle manager assign one or more number of partition to the peon, and also provide the sequence number from which the consumer has to read. Consumer seeks to that sequence number and continuously pull and read the data from the partition. Okay, so I'll just mention the steps here. The middle manager first assign the partition, then the consumer, the program within the client library within the task, seek the sequence number. Then it continuously poll the broker, retrieve the data one by one. Then after that, it pushes to the deep storage. Once it has enough data consumed from the broker based on some criteria. So let's say one of the criteria is the task duration. We will discuss more this criteria more in detail in the coming slide. Once it consumes enough data, it pushes that into deep storage. Then peon hand over the ingestion to the next peon. Before handover to the next peon, it pushes the segment to the deep storage and commit the sequence number to the metadata, so that the next peon can get the sequence number from the metadata and continue reading the data from the Kafka broker. This is cool. Okay, let's see. Let's discuss what are the challenges. Okay, the Druid ingestion task creates segment based on interval. So late arrival of data will result in multiple active real-time interval. We are going to discuss this in the coming slide. Let's skip through. Another challenge is the task failure due to out of memory. Accommodating spike in data can also cause some issues. So we always size it for the spike, right? Not for the normal duration, normal workload. High number of real-time queries or large variation in the number of queries on real-time as well as historical can cause issues. Yeah, let's discuss in detail each challenge. This is a sample case that the data is ingested just after 5 o'clock. Assume the real-time span is defined as 1 hour. That is, the data between 5 o'clock to 6 o'clock is stored in a segment. As the time moves over 6 o'clock, the data with timestamp greater than 6 o'clock will start coming in, and one new segment will get allocated for storing the data. So that, okay, now look at this. Assume if your data is coming late, that is, you have more active segments, as you can see, for the real-time ingestion. Since the late arrival of data usually is very less in number when it compares to the normal duration, normal real time, in that case, each segment will end up in small number of rows. If you look at the figure, you look at the image, this is less than 300 records are coming, which are late, whereas 15,000 records are the real-time one. Okay, this can be the case even for late arrival as well as for early arrival of the data. Okay, so this will result in small segment. This graph is an example of our memory footprint when the data is coming late. So why it is coming late, why it is the memory is increased, because more active segments are getting ingested. So we will cover this topic in the coming slide. Often it's a practice to configure more number of tasks to ingest data from Kafka to handle spike. The data used to be less during normal period or non-spike period. In this case, each task will get less number of rows. And at the end of the interval, each task creates at least one segment with whatever data it reads from the Kafka partition. So if you handle for spike, you may end up small segment. So this is another typical example of small segment scenario. How do we get out of it? We will discuss this in coming slide. Well, so often this is the question: why small segments are bad? In Druid, data is dictionary encoded. That means each segment creates a dictionary. The size of the dictionary depends on the cardinality of the columns. Higher the cardinality, higher will be the dictionary size. When the Druid process queries, the data from the segment is retrieved, and each thread read one segment and create an intermediate result. The intermediate result from each segment is later combined and sent to the broker. This merge is done by one thread. If the segments are smaller and larger in number, there will be more intermediate result. Historical process will take more time to merge the result. This will lead to higher latency or slower query performance. In some use case, the requirement is to query the near real-time data. This will cause high CPU in real-time node. Even if the number of queries may remain the same, but the type of queries can change. Example, time series query have low resource utilization compared to other query types. Then comes the token, then comes the group by. Sometimes the real-time node ingests a lot of data to its max capacity. And there can be the case that a lot of objects are created and there is not enough memory, and the GC will happen. I mean, a lot of more GC will happen in that node, which ultimately cause bad performance. I would like to outline three possible options for handling data. Reject late arrival or early arrival of data beyond a threshold. That's one option. This can be done by setting late message rejection start date time or late message rejection period. The same configuration is available for early message rejection period as well. That's option number one. Option number two, increase the segment granularity to a higher duration. For example, if your data is coming late for a day, then increase the segment granularity to day. But this cannot be increased beyond a certain limit. The challenge is if the data is coming 7 days, maybe we cannot keep 7 days segment granularity. So the idea here is you need to take a decision. What is your tolerance level? But often customer complains, no, I don't want to throw away my late data. I want that data. Fine. Other option we can think of is store the data, late data as a file and rely on batch ingestion to ingest those late data. Maybe if the data is coming late more than a day, maybe another 6 hour or 8 hours, once in 8 hours, you can ingest as a batch. It's fine. Okay. Let us see how to avoid out of memory. It's commonly seen that the ingesting large event or ingestion with data sketches use more memory. It's a good practice to set max byte in memory or max rows in memory. This ensures that data will be persisted to disk once the peon reaches the limit. How do we know the memory allocated to the peon task is enough? Watch out for the GC time. You will see more GC if the memory allocated is not optimal. Rule of thumb, allocate more memory if GC time is more than 5 to 10 seconds per minute. How fast I can ingest the data from Kafka? One of the common questions used, Druid ask. Druid polls the Kafka partition we have seen in the previous slide. Druid polls the Kafka partition in every frequent interval and get the data. So by default, this value is 100 milliseconds. You can configure this by setting poll timeout in the supervisor spec, which means this is a configurable parameter. You can increase and decrease the way you want. If you are decreasing it, Druid reads data fast, but this will hog your Kafka. This means once the data is available in Kafka and it's arrived in Druid, you can query that in 100 milliseconds. Like any other Kafka consumer, the consumer properties can be configured under consumer properties in the supervisor spec. I found the following 4 consumer property useful in tuning the Kafka client based on your workload. If there is a large number of rows to be ingested, instead of holding the data till the task duration is over, let's say your task duration is 1 hour, you can push that workload to historical. So historical is designed to handle more data, historical data. So our target is to push the segment as early as possible, but you need to take care. The segments are created in the real-time node. That means you need to ensure that the segments are properly sized before pushing to the historical. So it's a good practice to configure intermediate handoff period or max total rows. Once this limit is reached, entire segment will be pushed to the historical. The common practice, often the best practice, is to set the Druid processing num threads to be 2. This is primarily considering the fact that one thread handles the ingestion and another thread handles the query. However, there is no CPU isolation, but this is a good approach to help to reduce thrashing of your CPU. So now, if the queries are more real-time in nature, you could increase the Druid processing num threads to a higher value. Monitor Druid metric, query time, and query wait time for tuning. So based on this, you can take a decision whether to increase or decrease the num threads. As discussed earlier in the slide, small segment can happen in the cluster. This will impact the query performance. one of the best practice is to size the segment such a way that each segment will have 5 million rows or a size between 300 to 700 MB. This can be done using configuring the auto compaction. Each time when the data is ingested, you need to take care one more thing. The time interval is locked, which means no other task is allowed to write the data. Compaction is also kind of batch indexing, where multiple segments are read and written as a single segment. So one of the key points to take care is while defining the compaction, you should skip for the latest interval by setting the skip offset from latest. Otherwise, compaction will fail since it cannot acquire the segment lock. Okay, let's start concluding. So we discussed about how real-time ingestion worked. We also discussed the common challenges in real-time ingestion. We discussed about out of order, maybe just a common scenario. We discussed about how to handle the or configure the auto compaction so that even if you size it for a spike and small segments are generated, that will be compacted well at the end of the time duration task interval. A high volume of real-time queries. How do we handle? We need to change the num threads. And we have seen the best practices, rejecting the late arrival of data, early arrival of data, and configuring auto compaction, offloading the data to historical and Kafka consumer, tuning parameters, and real-time query performance, how we can increase the num threads. Thank you for your support, and thank you for this opportunity. Any questions?